All right, now let's talk about 1.5 complex numbers. And we're going to learn about complex numbers or imaginary numbers as I. We're going to also look at combining and multiplying complex numbers. We're going to use conjugates to get the imaginary number or the complex form into a standard form. And we're going to find some complex solutions to quadratic equations. So the very first thing that I have to introduce you to is, what is the definition of I? It's just the square root of -1, and it's clear to see that that will never work, right? Now, if I write this as -1 all to the 1/2 power, then I'm hoping you see the pattern that emerges. So if I ask for I squared, well, that's just going to be the square root of -1 times the square root of -1, or, well, that's just going to be what? Well, what is the square root of -1 times the square root of -1? Well, that just means that it's I times I, but more importantly, it becomes easy to see that this is in fact, oops, I didn't change the color here. Or just, I didn't know the colors were, or simply -1. Maybe I'll summarize over here in a second. And then let's look at I cubed. Well, that's just 3 i's being multiplied together. So we already know that this is I squared, and it's times I. So this looks like it's just going to be -1 times I, or a negative I. And I to the 4th, well, that's just I cubed times I. So that's just negative I times I. And we already know what I times I is, and that's I squared, so this looks like it's going to be a +1. Now, if you do the pattern, you start to see what it is. Every 4th one, we're going to start to repeat. So if you do, just for quick sake, I to the 5th, it's going to be I to the 4th times I, and I to the 4th was 1 times I, as just I. So notice we're starting to recycle, and we can just keep going through that pattern. So I is just the square root of -1. I squared is always going to be -1. I cubed and multiples of that are always going to be negative I, and I to the 4th will always be 1. So I call this, the I chart. Get it? So I wrote it like an I, but it's I. Okay. Anyway, let's move on. So the general equation for complex numbers, or the standard form for a complex number, is the real number that we have here and the pure imaginary here. Okay. So it's just put into this perspective, and we're just showing that if the two complex numbers are equal, if and only if C is equal to A and B is equal to D. So it's just saying that A and C have to be the same, and B and D have to be the same. So combining complex numbers, no real secret. You just combine like terms. So if I have something like 2 plus 3i plus 1 plus, 2i, then this is just 3 plus 5i. Okay. Multiplying, I would do it just like classic multiplication. So if we did that same problem as 2 plus 3i, and we're multiplying, not 3, we're multiplying by 1 plus 2i. So I'll just remind you. And then this would be 2 plus 3i plus 4i plus 6i squared. And when we combine all that, what we're going to end up with is 2 plus 7i plus, well, 6i squared. And, well, if we go and remind ourselves what I squared is, being -1. So then the standard form for this is going to be -4 plus 7i. Okay. Using the conjugate to rationalize, so if we have some complex in the denominator in this form, then the conjugate is this form. So all we're saying is change the signs, really, is what we're looking at. So if there is an addition, then the conjugate is the same thing, except that it's subtraction. Okay? And the product, you know, the specialized products do work as well, and that's just showing the difference of the two perfect squares in this example here. Okay, and what it does is it allows us to get rid of the internal I components. So notice that there are no single i's being around here. Okay. So what we're going to do is do an example real quick, and we're going to write this in standard form. So the only thing that we have to do is multiply numerator and denominator by the conjugate. So that would be 1 plus 2i in both numerator and denominator. Well, the denominator is going to be really easy to put together now, because that's just going to be the difference of the two squares. So that's just going to be 1 squared minus 2i squared. And now we can do that, the product of 6 minus 7i times 1 plus 2i. And let's multiply. So that's 6 minus 7i plus 12i minus 14. So this looks like it's 6 plus 5i minus 14. Oh, sorry, minus 14i squared. Almost lost that there for a second. So now what do we have to do? We have to convert this I squared to the -1, which it equals. So then if I go back up here, this equals now 6 plus 5i plus 14. So this looks like it's 5i plus 20. Or if we wanted to factor out the 5, we could say it's 5 times the quantity I plus 4. And so that would go up here. Alright, so let's do some just crunching, a little more number crunching on this, just to make it nicer and more simplified. So what we have at this point is that this, writing it in standard form, is going to equal 5 times I plus 4. Now that might have been an unnecessary move, but maybe not. We'll see. And that'll just be 1, because 1 squared is that, minus, looks like 4i squared. So if we have this, then this is going to tell us that this is equal to 5 times the quantity I plus 4 divided by 1 plus 4, which then is clear to see that all of this crunches down to I plus 4. So the standard form for this, so the standard for this problem is I plus 4. And where did I get I plus 4? Well, because that's 5 over 5, and they just cancel out. Alright, so let's look at another example of writing in standard form for the complex numbers. And what we have here is a simple product, but you'll notice that we don't have any i's around. So what we have to do is generate the i's first. So we got to get the i's together here. So we'll just rewrite it here for a second and say this is 3 plus the square root of 5 times the square root of -1 all times 7 minus, well, the square root of 10 times the square root of -1. So we know that -1 is really, the square root of -1 is really I. So this goes down to 3 plus root 5I, and it's on the outside, that's what making that little lip there, times 7 minus the square root of 10I. Now that we've generated this, we can now generate the product very easy. So I'm just going to put this in the numerator here, or at the top, I guess. It's not really a numerator. Times 3 plus root 5I. So again, it's just classic multiplication. So 7 times 3, 21. 3 times that piece, well, that one's positive, one's negative, so it's negative 3 root 10I. And then we have this, which is plus, because they're both positive, 7 root 5I. And then we have the last beast, which is simply going to be plus because they're both the same there, and this will be the square root of 5 times the square root of 10 times I squared. And now we're going to do the combination. Alright, so doing the combination, we have 21 minus 3 root 10I plus 7 root 5I plus root 50I squared. Now we can't combine these, right, because they don't have the same roots. But perhaps we can do something about that in a moment and maybe do some trickery, okay? So we can maybe do it. But let's take this as it appears right now. And let's do some number crunching. So what I'm going to do is I'm just going to rewrite all of this junk again. Except what am I going to change? Maybe I should do it this way. What am I going to change this sign to now because of this I squared? Yeah, you got it. A subtraction, or the negative, right? And let's just use this in black still, the square root of 50. Okay? So now let's do a little more work here and see if we can do a couple more tricky things here and see what we can do to come up with a much better way to represent this solution. All right, so now that we've done the combination, remember we can't combine these because they don't have the same roots. Now all we have to do is put the like things together. So, because all it has to do is put this in standard form. So because these two terms have i's in them, I'm going to group them together. And, well, you'll see in a second. So I'm just going to rewrite this. And why am I changing this to negative root 50? Well, because what does I squared really become? Well, it's really -1, right? So I'm just changing that addition. So I'm going to leave this here as a group, and then I'm going to add, let's see, well, I got to put all these numbers together, so it'll be 7 root 5I minus 3 root 10I. And what I'm going to do is I'm going to group these together, just so we can see that this is the complex portion of our answer. Okay? So all we have to do is really pretty much just factor it out and record it. So let's do that. We'll simplify this in a second. Let's just factor out the I here. So this is 7 root 5 minus 3 root 10 all times I. So all we did was factor an I out. And I'll rewrite this as 21 minus root 50. And I'll group it. But we know that the square root of 50 is really the square root of 25 times 2. So this looks like it's going to be 21 minus 5 root 2, all plus 7 root 5 minus 3 root 10i. And this would be the standard form for here. So the standard form would be in here. So this and this are the same darn thing. Alright, so now let's look at finding complex solution for quadratics. My advice is to use the quadratic formula and do some substitutions, knowing that this is the standard ax squared plus bx plus c is equal to 0. So all I did was make a list of a, b, and c values. Now b is negative 2. So I'm just going to insert these into the formula by just rewriting everything. And I might have to make this a little longer here. And then divide by that. So a goes here and here. B is negative 2, goes here, and C is 2. So if this is the case, this just breaks down to all of this. Well, that's going to be 4 minus, well, that looks like 8 all over 2. So now if we break this down, we notice that here's the complex. This is the square root of negative 4. And this is just the square root of 4 times the square root of negative 1, or I. So this looks like it's going to be 2 plus or minus 2i divided by 2. And simplified, it's just 1 plus or minus I.